Hello everyone and welcome to today's Explainer. Today we are demystifying AC motor math with a step-by-step breakdown. We're tackling the true mathematical heartbeat of the modern world, the three-phase induction motor. Invented by Nikola Tesla well over a century ago, these machines are absolutely the workhorses of modern industry. Now, if a page of handwritten electrical equations usually makes you break a sweat, do not worry. We're going to transform this daunting math into a totally solvable, deeply satisfying puzzle.
So, can we actually solve this three-phase motor problem? Absolutely. Our central challenge today is this specific case, and to tackle it, we're basically going to act like engineering detectives. We'll methodically identify our knowns, find the exact right formulas, and crack this mathematical case wide open.
Okay, let's dive right into it. Take a look at this. It's a classic question 5 on an engineering exam, and it is exactly what we're solving today. I know, a giant block of text and symbols looks pretty intimidating right off the bat, but notice that super helpful diagram on the right? It grounds us in reality, showing our three-phase supply feeding directly into the motor. We are going to figure out the exact physics happening inside that machine.
To conquer a massive problem like this, you really have to chop it down to size. Looking closely at the prompt, it's actually just asking us for three very specific things: finding the rotor speed, finding the rotor frequency, and finally, finding the rotor copper loss. By isolating these requests, we've instantly broken this big, scary problem down into three entirely manageable targeted goals.
Step 1. Extracting the clues. Before we even think about touching a calculator, we need to gather our facts and lower our cognitive load. Straight from the source document, here's what we know right out of the gate. We've got a synchronous speed, that's our n's, sitting at 1500 RPM. Our slip, or s, is 4%, which will convert to the decimal 0.04. We're assuming a standard supply frequency, f, of 50 Hz, which is super common in many parts of the world. And our rotor input power, P2, is 30 kilowatts. Boom. With everything laid out cleanly like this, the problem is honestly already half solved. All right, let's tackle objective 1. How do we actually find the rotor speed represented by the letter n? Well, here is our formula, and the logic behind it is just beautiful. N equals ns times 1 minus s. See, synchronous speed is basically the theoretical maximum speed of the magnetic field, right? And that slip is just a measure of how much the physical rotor lags behind it. So we literally just plug in our 1500 RPM for the synchronous speed and our 0.04 for the slip.
Let's walk through that arithmetic real quick. 1 minus 0.04 gives us 0.96. Multiply our 1500 synchronous speed by that 0.96, and there we go, 1440 revolutions per minute. Our physical rotor is spinning at exactly 1440 RPM. Objective 1 is officially in the books.
Keeping that momentum going, what about the rotor frequency, denoted as FR? If you thought that last formula was straightforward, you are going to love this one. It's a surprisingly simple equation. Rotor frequency FR simply equals our slip S times the supply frequency F. That is it. All we have to do is multiply our given 0.04 slip by our assumed 50 Hz supply frequency.
Just a tiny bit of mental math here, 4% of 50, and it gives us a beautifully clean answer of exactly 2 Hz. Now, this exceptionally low frequency is actually exactly what you'd expect to see in the rotor of a healthy, running induction motor. And, just like that, we've totally knocked out the second objective. This sets up the final piece of our puzzle. Finally, we have to ask, what is the rotor copper loss, designated as PCU? And remember, the original prompt gave us one final clue for this. We're supposed to assume a 30 kilowatt rotor input power.
What's really fascinating here is how that slip variable shows up yet again. It is incredibly foundational to the operation of an induction motor. It dictates not just speed and frequency, but also power lost as heat. So the formula is just rotor copper loss equals slip times the rotor input power. We simply take our 0.04 slip and multiply it by that 30 kilowatt input power.
Let's crunch this last set of numbers together, 0.04 times 30. If you just move the decimal over and multiply 4 by 0.3, you land safely on our ultimate answer, 1.2 kilowatts. That right there is our rotor copper loss. The final breakdown. Let's see how all of our detective work paid off. Just look at how cleanly this dismantles a complex problem. Rotor speed, 1440 RPM. Rotor frequency, 2 Hz. Rotor copper loss, 1.2 kilowatts. Identifying your variables up front and matching them to the right relationships seriously makes all the difference in the world. To bring this whole thing full circle, let's take one last look at that original source document. Notice those final answers neatly underlined in blue ink by the author at the bottom: 1440 RPM, 2 Hz, and 1.2 kilowatts. We have successfully mapped out this entire page, validating every single step of this mathematical journey along the way.
So, which complex formula will you break down next? Honestly, if you can apply this kind of logical, step-by-step breakdown to the physics of an industrial AC motor, you can unravel almost any technical challenge. These simple relationships of slip, speed, and power dictate the function of everything from massive factory conveyor belts to modern electric cars. The next time you face a wall of intimidating technical information, just remember, extract your clues one by one, tackle it one formula at a time, and you've got this. Thanks so much for joining me on this explainer, and keep that curiosity alive.